Hello, everyone. Um, in this third lecture for this last week of the course, we are resuming our exploration of the Titanic dataset. Um, just as a reminder, we are trying to learn, using a machine learning model, who was likely to survive the Titanic disaster, and who was likely to perish based on such information as the ticket class, whether they were a man or a woman, their age, how many traveling companions they had, what fare they paid, and where they embarked. So, as of the previous lecture where we left off, we had managed to do a number of things. Not only had we filled in missing values in the data, we had removed some columns that were probably useless or were missing so much data that we couldn't possibly impute the missing values. So often when we're missing values and we fill them in, that's called imputation. And we also converted some of our categorical variables into numerical format. So with something like sex, this is quite easy. We had two options, so we could just label them 0 and 1. But for something with more than two options, such as embarked, which had S, C, and Q, we used a method known as one-hot encoding. Alongside this notebook, we've been developing a Python script that will be sort of a more realistic format for how we might develop this in a professional setting where this Python script might be used by a web framework like Flask to run an application on the web. And in fact, that's where I plan to build towards over the next two lectures. So let's resume finishing up this machine learning task. So now we have our training data in the format we would like. Let's go ahead and split it up into the labels and the feature matrix. So the labels are this survived column, so we'll pop that out of the data frame. I'm experiencing some kind of error, so I'm going to refresh the page here. And I hit a name error down here, so apparently my kernel has reset. So I'm going to need to rerun some of these things. encountering all sorts of problems this morning. Not quite sure what the issue was with that error that just popped up, but going to forge ahead. Okay, so now our training data has, oh right, and we also drop passenger ID, since that has no useful information. So now we have only the variables that we think will be useful in the numerical format we want, and we have our labels for each row, whether someone survived or not. So now we're going to build up our machine learning model. It's always a good idea to scale our data so that all of our features are on the same scale. We also will want to use a pipeline to combine any transformers and estimators into a single scikit-learn object that we can use with things like grid search. We'll want to use grid search. And we'll have to select an estimator. So for now, why don't we begin with logistic regression? It's very simple. And if we need a more complex model, we can try that. So we're going to have our model consist of a scalar and a logistic regression. And we're going to do a grid search. And our parameter grid, well, we'll have to look at the hyperparameters of this logistic regression. And it really only has two hyperparameters that are particularly meaningful. So logistic regression is regularized. We can choose between the L2 regularization and L1 regularization. So to remind you, this changes the way that we calculate the penalty associated with the coefficients. L2 biases our coefficients towards 0. L1 can actually force them to be 0. we also can choose the strength of the regularization, which is this C parameter. It gives us the inverse of the regularization strength. So we'll say for the logistic regressor, we're going to try two penalties, L1, L2, and a few values for C, 0.01, 0.1, 1, 10. We're going to use 5-fold cross-validation. We'll use 4 CPU cores to run this grid search. Am I missing any other arguments to grid search? No, that's it. AID. So we can go ahead and fit the grid search to our training data. So it's done. Let's have a look at what the best params were. So it looks like the L1 penalty with a strength of 10 performed best. I'm going to redo the grid search just since 10 was the maximum regression strength. I'm going to try, or the maximum inverse regression strength. I'm going to further search 100 and 1,000 to see if those strengths might be even better still. But it looks like about 10 is the value we want. So now we have our finished model. We can just use the grid search results as our model. So if we wanted to make predictions, we could predict on test. But we haven't performed all the cleaning operations to test that we've performed for train. So we'll need to go ahead, remove name, passenger ID, convert embarked, remove cabin, all those things that we did with the training data. Since we have the training data here, or since we have those operations in functions in our Python script, I'm actually going to add this modeling step to our Python script, and then we will perform not only the fitting, but the prediction in the Python script, and we'll have that write the results to the file, and then we could upload the results to Kaggle. So the results are illustrated by this gender submission CSV. Which, as we can which, as we can see here, simply has the passenger ID and survived columns. So this is the format we need to use for our results. So we're going to build the model. We'll need to additionally use these imports. And now, to make predictions, we will read in our test data. Apply all the same transformations that we use for the training data. We're going to open up a file for results. Actually, let's do it slightly differently. So we'll make our predictions. And then we will create a data frame . And we're going to save that data frame to a file. So let's have a look at what this does. All we did was transfer our new code from the notebook to our Python script, and I slightly reorganized it. So I made this new function, build model, which simply constructs the pipeline. Then I put the grid search piece down here in the main portion of the script. And then I added the steps where we read in the CS test data, we clean it up, and we make our predictions. So in fact, we don't even need to, since we've already done a grid search, we don't need to do this piece. We already know what the best params are. And I will just put them in the model instantiation, the model construction. So remember, we wanted penalty L1 and an inverse regularization strength of 10. Now if we run this script, yes, I just deleted GS. So here we'll take model. So we ran into an issue. Value error input contains nan, infinity, or value too large for data type float. So our test data didn't quite get treated as we had hoped. It didn't remove all the nans, most likely. So let's have a look at our test data. So here's our test data, and if we ask where the null values are, there is additionally one null value in the test data for fair. So we're additionally going to need some code that computes or imputes the fare of one of the passengers for whom we are missing data. So we can do this the same way that we impute age based on class. We'll impute fare based on class in the exact same way. So I'm going to actually break out this piece into a new function. And I'm defining a new function, impute by class, which accepts the data frame as an argument as well as some field or column. And this column is what we will be imputing. So originally this was age, but we could want it to be fair. So here we'll just replace age with whatever column we want to impute. So now, by imputing the missing fare, we were able to eliminate any null values in the test data and actually make predictions and get some results. So here is our file of results. One thing to notice is we don't have the correct passenger IDs. So I don't think this is particularly elegant, but I'm going to, before I clean the test data, how do I want to accomplish this? Okay, yeah, so this is really inelegant, but I know that the correct passenger IDs are 892, or they start at 892, so we'll just make a range of numbers 892 to 892 plus the length of test. So this is not such a great way to do this. Better still might be length of train plus length of test. Still not very elegant, but this will do in a pinch. So I'm rerunning the Titanic script, which produces a new results.csv, and now we have almost the correct passenger IDs. I need a +1 here. Because passenger IDs started counting at 1 and not 0. So one more time I run the Titanic script. That makes my new results.csv. And so I have all these correct passenger IDs and predictions as to whether or not they survived. So here we can assess our work in two different ways. First of all, we can submit predictions. So on Kaggle, there is a button for submit predictions. We can submit our results.csv file. We can describe what we did. Dropped meaningless columns, including name, imputed missing age, fare, and embarked values, logistic regression with low L1 penalty. And here is our entry. So we scored 0.756, which is not too bad. It's 9,000th, but you know, quite a few people did worse. And if we look through the leaderboard, I know with this particular challenge, so quite a few people score 1 here, and these people definitely cheated. The record of who lived Oh. The record of who survived the Titanic sinking is a matter of public record. You can look up what the answers should be. I'm not particularly certain why anyone would want to cheat on this competition. There's no reward for winning, but nonetheless, some people do. And the highest accuracy that you can really get by legitimately competing and making a model is, I believe, around 80 to 85%. And people who score higher than that did something that was not entirely legitimate. So we're not so far off. We got 75% accuracy. We could have also, of course, split up our training data into a training set and a validation set, where we would have labels for the validation set that we could use to evaluate how our model performed. That would be how we would typically do this. Since Kaggle has labels for the test set, we can simply submit our answers and it will grade our predictions on the test set. So, let's go ahead and, first of all, check in our project into Git. So in this commit, we added model, made predictions. So one thing I want to address is we've only been checking in this Titanic.py file. But we have a few other files here, train and test and results. What should we do with those? This py-c file is just a kind of pseudo-compiled Python file that the interpreter makes in order to speed up running the Python script multiple times. We're not going to worry about that. But these CSVs where we store our data, do we want to check these into Git or do something else with them? So opinions vary about this, but often our data will be quite large and will be static. So we won't usually really need version control on the data because the data typically will not change. And additionally, since these are tend to be large files, we don't typically want to have these stored online on GitHub, and so that whenever someone wants to replicate our project, they need to download the data from GitHub. Since the data is easily available from Kaggle, and we would rather just tell people where to find this, and they can download it themselves. So we're going to make a data directory, and we're going to move the CSV files into the data directory. Which means, of course, now when we read in test and train, we need to tell it that these things live in the data directory. also going to write our results to the data directory. And if we do git status, it's going to tell us that we haven't tracked this data directory as well as this PyC file. We might not want to be told that all the time because we don't intend to track these files. We don't intend to check the data into version control. And this is just like a file that's automatically created that we don't care about, so we don't intend to track this file either. So we can create a git ignore file and tell it to ignore the data directory, as well as anything ending in PyC. So we put that in a file called gitignore, .gitignore, and if we do git status now, it is ignoring the data directory and this Titanic PyC file. We'll actually commit our git ignore. And update our titanic.py file to reflect that we moved the data to this data directory. And now when we do git status, we get a nice nothing to commit working directory clean message, which lets us know that everything is kind of in the proper place that we intend for it, and nothing has changed since we last made a commit. So in the last few minutes, I'm going to cover how we put this on GitHub to share with others. So under my repositories, I have a bunch of different projects I've worked on, but I don't have anything relating to this Titanic competition. So I'm going to make a new remote repository on GitHub. I'll call it Titanic. I'll give it a little description, and I'll create this repository. So this is the repository. It's currently empty. We need to push our repository on our local machine to this remote. And it actually tells us how to do that right here. Push an existing repository from the command line. So we're going to, first of all, tell git that there is a remote repository that should be connected to this one. So we add a remote repository. We give it the name origin. This is a very strong convention. It's very typical to name the remote repository origin. I don't know why, but this is a strongly followed convention with GitHub. And we tell it where this remote repository lives. So it lives on github.com at the DZB user and then Titanic repository. And then once we've added that remote, we can push our current repository to the master branch of our remote repository. So I haven't talked about branches yet. I will show that next time as we explore some different development paths we could take, such as trying to improve our score by improving our modeling and our data handling. Another development branch we'll consider is moving the data transformations into scikit-learn. And finally, we'll also consider a development branch for creating a web app based on our work here. So I'll continue with that in the next lecture.